There are three topics now I want to talk about with Logit models, which shows the extent to which Logit models are useful and their limitations. Taste variation, how to deal with panel data, and substitution patterns. In each of these cases, Logit models will take you a part of the distance, but maybe not the full distance that you want to go. And so you need to know how far you can go with Logit models and how far you can't go, and when you need to turn to a different kind of model. So first of all, taste variation. Generally, the mainstay of microeconomics is that different people have different preferences, and we would like to be able to represent what those preferences are, or what the distribution of those preferences is in the population. With the Logit model, you can do that. Just to summarize the result, Logit models allow you to represent the part of taste variation that is systematic, that you can relate to observed factors, but will not allow you to handle or represent taste variation that is random. Okay? So the difference is whether the taste variation is systematic, related to factors that you as a researcher can observe, versus being random, related to things that you don't observe. Okay? It can handle the first of those, but not the second. So let's use an example. Suppose we have mode to work, and we've got the time that it takes to go to work by each mode times the coefficient, and the cost, let's call it CIN. Okay. And let's now let this coefficient, you could generalize this obviously, but let the coefficient of time vary across people. We know that different people value their time differently. Some people are in a rush about everything. Some people, you know, just life's easy. Who cares if I sit in this traffic the rest of the day? The question is, what kind of variation in this coefficient can you capture? If it's systematic, all it means is that you change the specification of the model. Suppose this is equal to, let's say, theta times, what do you think would mean, let's say it's income, or your wage rate, income. So people that have a high income have a high value of time. People with low income have a lower value of time. Probably is not true, but the point here is that it's systematically related to some variable that you can observe. In that situation, it's very easy. You just substitute in, and Logit can handle it. The variable that you enter the model is the time it takes to go by the mode times the person's income. Okay? And the coefficient then is interpreted as the relationship of income to the value of time. You could then, of course, have another term, say a constant term on this, so that there's a value of time that on average, and then this is average income, and so it's variation around that. Then you would have, by substituting that in, time by itself and an interaction of time times income. So it is true that Logit models can handle taste variation, as long as that taste variation is systematic. However, if it's random, you get into problems. What if this is equal to systematic component plus a random amount, which we don't observe? Okay? We could say it's distributed in a certain way, but we don't know what the actual value is. And then substituting that in, we get the systematic component entering just as before. We also have our cost. But now we've got this error term, this new random part. And this is now our error term in the model. It's composed of our original error term and time times a random factor. There is no way that this can fit into a Logit. No matter what error distribution you give for this and for this, you can't fit it into a Logit. A Logit assumes this whole thing is IID, meaning that it's independent over alternatives and independent over all people. But as we've specified it, that's impossible. Insofar as the time on a mode for one mode is correlated, related to the time, let's just state it explicitly. It's not homoscedastic because the variance of this error term EIN star is equal to the variance of eta times TIN squared plus whatever the variance of your original epsilon is. Insofar as this varies over people or over alternatives, then it's not going to have the same, this error term is not going to have the same variance for all people and for all alternatives. Similarly, you can calculate the covariance between two alternatives. It'll depend on the time for the two alternatives multiplied by each other. And hence, it's not zero covariance. So they're not independent over alternatives. They're not identical over alternatives and people. So you simply cannot capture. If you believe there's random taste variation, a logit model is inappropriate. There's no way you can squash it into a logit model, a standard logit model. So that's the first thing. Taste variation, it can handle systematic taste variation, but not random taste variation. Yeah?
Presumably you wouldn't really know that a priori. Is there a way you can test it?
Well, yes, you go to a model that actually can incorporate this and test the hypothesis that the variance of this term is zero. So it's the standard way of going to an unrestricted model and testing down to the restricted. Within a logit context, it would be extremely hard to do. You can get residuals on these. So that you can calculate a predicted residual for each person and then test a hypothesis that those have the same variance. But it's more difficult to do nowadays. That's when you didn't have the mixed logit models, that's what you had to do. And that also tests for a whole lot of sources of heteroscedasticity, not just a specific type of taste variation. Okay, so that's number one. Number two, panel data. Often you will have a series of choices that a decision maker has faced, and you want to represent the process by which that series of decisions is made. And in fact, you might want to incorporate the idea that a decision at one point in time can affect the decision in the next point in time. State dependence, or what you do in one period has an impact on what you do in the next period. Under the maintained assumption in a logit model that the error term is identically and independently distributed over every possible variation over time, alternatives, and people, then you could do everything you want with panel data. Okay? So a logit model under that very severe restriction allows you to capture anything you want with panel data. However, it does not allow the possibility that the errors are serially correlated over time. That's a severe restriction. So let me kind of write down the general formulation here. The alternative utility from an alternative I in time period t for person n is equal to something that's observed. And I'm going to put just a lag-dependent variable in here. This is only as illustration. You could do all kinds of specifications of the process by which decisions change over time. But as an illustration, let's say there's just a lag-dependent variable. So this is the dependent variable saying whether the person chose alternative I in the previous period, okay, and then an error term. In general, we will use this, this notation concept later for other models, but a sequence of choices can be described as a vector I. You could think of it as I wiggle, tilde, which is the chosen alternative in the first period. I'm sorry. The alternative in some particular alternative in the first period, an alternative in the second period, on up to an alternative in the last period. So this is a particular alternative in the first period and a particular one in the second period all the way up to the last period. This is a vector that represents that sequence of decisions. The probability that person n makes a particular sequence of decisions can always be represented, we'll use this other times for more general models also, as the probability of alternative 1, I'm sorry, the probability that they choose alternative I in the first period times the probability that they choose alternative I2 in the second period given I1 in the first period. I'm going to leave the ends out, so just leave them out. On up to the probability of I capital T given I t minus 1. Okay. So you can state it as the probability of, this is like a marginal probability in conditionals, and you can just represent the joint probability of the whole sequence as that. Now the question becomes, how can you represent each of these probabilities? Under the Logit assumption, each of these probabilities is extremely simple. Essentially, we're assuming that this error term is independent over alternatives, time, and people. Okay? So we have no correlation anywhere going on. Under that situation, then the probability of any particular alternative in a given time period, given what they did in the previous time period, is simply the Logit formula with the lag-dependent variable included. Okay. Why is that? Essentially, this conditioning does not change the probability of a given alternative. The only reason a conditional probability is different than an unconditional probability is if that conditioning gives us information that is usable. And yet, there's no information that can tell us anything about these error terms in the current period. The previous value of the error terms, which affected what the person made in the choice they made in the previous period, don't carry forward to the current period. So the fact that each error term is independent allows us to include lag-dependent variables without a problem. This is exactly analogous to regression models where it's okay to add a lag-dependent variable if you don't have serial correlation. You still have consistency. It's only when serial correlation comes in that you have inconsistency from ordinary least squares applied with a lag-dependent variable. So this is the analog to it. You can then use Logit models, of course, even if you're not interested in state dependence on how things change, how choices in one period affect choices in the next period, and you just enter new variables each time representing the behavior in that time. So Logit models, if you're able to make the assumption that the error terms, the things you don't observe, are not correlated over time, is very convenient. You essentially have each time period constitutes a new observation, and there's nothing new. You just have a longer data set with each decision maker in each time period constitutes an observation, and they're totally independent observations. You can add lag-dependent variables. So the limit here is for panel data, as long as you can represent the errors as being uncorrelated, independent each time, then you can represent any form of state dependence that you want or non-state dependence, and everything's fine. However, if your errors are correlated over time, you cannot do it within a Logit structure. These conditional probabilities do not reduce to Logits, and so you're just stuck there. So again, in each of these cases, you can kind of go part of the way, but not the full way. Now, the last one is the issue that has been raised most often with Logit on the limitations of Logit. Another way of calling this problem or the substitution issues is IIA, independence from irrelevant alternatives. Logit has a property which can make the substitution patterns that come from it extremely unrealistic in some situations. In other situations, it might be quite realistic. Let's look at the ratio of two probabilities. Probability of I, probability of alternative K. Simply put in the Logit formula. All that over This is k now. The denominators cancel out because they've got the same denominators. So the ratio of two probabilities depends only on the observed factors relating to those two alternatives. It does not depend on anything else. This is an extremely restrictive setup. What this is telling you is the probability of choosing a Cadillac versus a Volkswagen, the relative odds of that, is independent of the price of a Buick. Another way to look at it is if the Buick changed its price, this model would predict that it draws the same proportion from Cadillac drivers as from Volkswagen drivers, so that their ratio of those two probabilities stays the same. In situations where this is true, then the Logit model is great. It has this this is what makes the Logit model so simple, is that it can be the probabilities, ratio of probabilities can be expressed in this way. But in cases where it's not true, it's a problem. So let me go through. How many of y'all know about the red bus, blue bus situation? Yeah, it's a common idea. I'm just going to go through it so everyone knows it. Actually, if you're ever using this in a job talk, or if you're testifying before court on it and using a Logit model, someone will ask you, well, what about the red bus, blue bus problem? And you'll need to be able to give a cogent answer. This is like so well known that everyone knows the problem with Logit with it. Red bus, blue bus problem. Suppose you have an initial situation where a person has a choice between a car and a red bus. So the two options are car and red bus. And let's say the person, from observed factors, the two look pretty much the same. So we get odds 50-50 chance of choosing each of them. Okay, so you estimate your model on these data. And then all of a sudden, somehow a blue bus is created by the transit agency. And it has the same observed characteristics as the red bus. Same time to get to work, same cost, and everything. A Logit model will forecast that the blue bus will, since it's exactly like the red bus, will end up with the same probability as the red bus. These two are exactly the same, so they have to have the same probability. And since the ratio of these two probabilities is the same, independent of what's going on with other alternatives, the blue bus, this ratio has to stay the same. The only way that can occur is if you give a third to each. So these two have the same probability, and the ratio of these probabilities, which is 1, stays the same. That means it's drawing the same proportion. This new blue bus is going to pull the same proportion of people from a red bus as it does from car. That's highly unlikely. What in reality will occur, I imagine, most people imagine, is that the red bus, blue bus, if it's exactly like the red bus, people who chose car have already decided they like car better than a red bus. Those people are still going to like car better than this blue bus because the blue bus is exactly like the red bus. Ain't nothing new here. So all the people taking car will stay taking car, and half the people taking red bus will now end up taking a blue. They'll just like flip a coin because you don't care what color it is. So the true probabilities will be like this. What this is actually representative of is the problem in a Logit model that the error terms are independent across alternatives. What actually is happening is that the unobserved factors that give rise to these probabilities are correlated over these two. They're exactly the same, so in a sense their correlation is perfect, 1, and not correlated with car. Okay? So it's the inability of Logit to capture the fact that unobserved factors that drive these probabilities have correlations in them. Okay? So a Logit model will overpredict alternatives that have that are similar to other alternatives. Another way to look at this this is the way to explain all this in terms of IIA property. This is called independence from irrelevant alternatives. Or IIA. Okay. Essentially, we're saying that this ratio is independent of alternatives that are irrelevant to I and k, that are not I and k. Okay. And that's what gives rise to this. Another way to think about this that I think is more intuitive and is a little bit implicit in what I've said is that this model implies proportionate substitution patterns. If you improve one alternative, it's going to draw necessarily from the other alternatives in proportion to the probabilities for those other alternatives. That simply means that your functional form is giving you the substitution patterns rather than the data. So you're not discovering substitution patterns. You are imposing them through the Logit formulation. And this can have an important effect. Let's say we have a large gas car. I do this with the government all the time. Small gas car, and we want to introduce an EV or subsidize an EV. Currently, market shares are even worse than this, but to make it look reasonable, let's say it's that EVs get 1% of the market. They're actually getting about 0.1%. But suppose we were to subsidize these EVs in a way that made people buy them more readily. And we subsidized them so much that this went up to 10%. This is mandated for California by the year 2003.
What is an EV?
Oh, an electric vehicle. Thank you. I don't know if you know, but California has these mandates that require that there be a certain number of electric vehicles on the road. And legally, the mandate is 10% by the year 2003, which is only 2 years from now. See how it happens. There's all these offsets, you know how these regulations get changed. But if this is going to go up like this, the only way it will happen within a Logit model is it draws twice as much from here as here. So that this ratio stays the same. Essentially, this will go to 6, and this will go to 3. So it takes 10% from each of these to be able to rise to 10% itself. Okay? That is not what's probably going to happen. The reality is far more that since an electric vehicle is generally a small vehicle, in fact, there haven't been any mid-size or large electric vehicles put up generally, it'll mainly draw from small gas cars. People who had small gas cars switch over. So maybe this would go to 0.26, and that picks up 7, and then the other 2 would come from here, and that would raise it up. Does that give it right? Yeah, that's more likely. From a policy perspective, this makes a tremendous difference. Under the Logit model, it looks like you're going to save a lot more gas than you're actually going to save. Because it looks like you're drawing all these people away from large cars, the gas guzzlers. Where in reality, that's not going to happen very much. It's mainly you're drawing them away from the gas sippers. So a policy analysis based on a Logit model where the substitution effects determine the impact of the policy can be seriously flawed. And what's more important here, I think, from a econometric point of view, is what I said before, that the Logit model imposes substitution patterns rather than learning what the substitution patterns are from the data. And generally what we want to do as economists is find out by observing behavior what those substitution patterns actually are. Okay, so the Logit model allows systematic taste variation but not random. Allows anything you want to do with state dependence on panel data as long as you have the assumption that the unobserved factors are independent over time. Okay? If they're not independent over time, you have to move to a different model. Substitution, it allows proportionate substitution, and as long as that's fine in your application, great. Otherwise, if you believe that substitution is non-proportional or you want to discover what it is, then you need to go to another model.
In that formula, in the denominator, in the dashboard,
Oh.
in the denominator, should it be dj or di?
This is J.
J.
The utility of choosing alternative J depends on whether you chose alternative J in the previous period. You could create other kinds of state dependence if you want. This is just a simple form. Okay, so that's everything I wanted to say about discrete choice and Logit models. Now I want to describe our computer exercise. and then turn it over to Grace so she can give you instructions on how to use the lab and hand out class accounts. Can y'all quickly pass these out? This is one page. There's 2 pages you should end up getting. There's more of them. One page has a lot of writing on it. Another page has only a little. There you go. Okay, each of you is going to get your computer account. And when you open it up, on the screen there'll be a data file, a data folder. And then within this data folder, it's just called data, is a series of problem sets. The one we're going to start with is ps01.logit. So within this ps01.logit, it has the data, computer programs, instructions, and everything for this first computer exercise. This is actually a virtual link. This is not your folder. So when you go into your account and go to this, you're not going to be able to write onto anything in this folder. You can only read from it. So what you want to do is when you're in your Unix prompt, first thing you want to do is make your own directory. And that'll make a directory up here level to data. Let's call it my PS1. Okay? And then you want to copy everything from here into this. There's all kinds of ways you can do this, but this is the brute force way. And these are very small data sets, so it doesn't matter if we've got thousands of them for each person. So you want to do a copy. I keep forgetting the direction of the slashes. You want to go to the root, and then data, and then ps01.logit /star.star. That tells it take everything from there, and then you want to put it, so you've got a space, and then whatever name you've given your directory. Okay, like my PS1. That copies everything from there into your own file, and then you can do whatever you want to with it. You can change the files as you need to. And then, best thing is to go into that. So do a cd to the name of your directory, and then do a list ls to make sure everything's there. Check to make sure it's the same as here. And then when you want to run your SST job, your SST files will all end in CMD. And the first one that you'll run is sample.cmd. And so at the Unix prompt, all you have to do is do SST space sample. It will look for the .cmd and choose the right one. And we'll run it for you. You can go just SST and do everything interactively. I find that it's extremely hard to do that because it's easier to just make your batch file, run it. If you get an error, you go in, edit your batch file, rerun it. And that way you don't, if you've made a mistake 3 rows back, you're working interactively, you lose track of where you were. Okay, on this first one, this page describes, SST is a program, probably the best one for running Logit models. It was developed by Jeff Dubin at Caltech. And this is the only week you need to do it, and it's just to show you how to get some ideas down on running Logit models. And you'll learn all the syntax you need quickly. Yeah?
Are there any more handouts?
There should be. I made like 50 some odd. Anyway, try to look on with someone else, because both of these pieces of paper are on, it's a file. So what you want to do is go to the README file. That's what this is, and it describes the data. So this is a data set that consists of 900 observations. We've got 5 alternatives, which represent the heating choices, or heating options that are available for those. Gas central, gas room, electric central, electric room, and heat pump. And then it has explanatory variables associated with each one. The important thing to realize here is that there is an installation cost and an operating cost associated with each of the 5 options, not just with the option that the person chose. So there's an installation cost 1, which is the cost of a gas central system. Installation cost 2, 3, 4, and 5. And similarly, there's an operating cost 1 to 5. So each person has an installation cost for each of the systems, which gives you the cost of what it would have cost to put that system into their house, even though they didn't put all 5 in. These are engineering estimates based on attributes of the house, contractor costs, and things like that. Similarly, operating cost. Then you have some variables that relate to the household, such as their income, the age of their head, and other factors that are listed. So you have a file that, if you're thinking of this in ASCII terms, is 900 rows, 1 observation apiece, and 1 value for each of these explanatory variables, with 5 costs representing the costs of each of the 5 systems. Then sample.cmd is an SST program. That's the second page you've got, which runs a badly specified model. This one's just so you have an example program here to use. And I want to run through this just so you'll know the syntax. The kind of syntax that's here is all you're ever going to need. Clear just tells it to get rid of anything that happens to be in the workspace. So if you're running the models over and over again and have produced variables that you don't want, it just makes sure you clear it. The load, the file that's loading in your data file, it's already as an SST file. It's not an ASCII file, so you can't look at it by just pulling up the data itself. You pull it into the program, and then you can look at it if you want. Spool file, that's your output file. Essentially, it's saying spool the output onto this file. And it opens it and saves all your results onto that sample.out, or whatever name you want to give. Then set statements are used to create new variables. What I created here was the ratio of installation cost to operating cost. There's no meaning in that variable. Can anyone think of a meaning that installation cost divided by operating cost would be? It's how many years it takes for the installation cost to be reached through annual operating cost. I don't know. Anyway, I did that just to show you how to create variables. And then you do an MNL, which is the multinomial logit. The dependent variable is listed in brackets after dep, and our dependent variable is dep var. It is a variable between 1 and 5 that identifies the chosen alternative. And then the only interesting thing about this that's different from standard regression is that in the independent variable list, you give it the name of the variable that you want to have a coefficient, installation cost, say. And for every variable, you have to specify what its value is going to be in each of the 5 alternatives. Because remember, we have probability of alternative I is equal to the factors that enter the first alternative and the factors that enter all the other alternatives in the denominator. So to calculate a probability, you need to know what the variable takes in each of the alternatives. So installation cost takes IC1 in the first alternative, 2, up to 5. And then the other variable does the same thing. So you give the name of the variable that you want. You can specify anything here. Your coefficient will be on this. And then you tell it what values to take in each of the 5 alternatives. Okay. A backslash at the end of the line means continue this command on to the next line. Otherwise, it takes the carriage return as the end of a command. The probability subop, as I've got it listed here, or in general what it does is you can specify the names you want for the probabilities that are calculated by the model. Okay. Jeff Dubin did this to save a little space. I thought it was silly, but the first alternative you can't get the probability for. So you're labeling the second, third, fourth, and fifth alternatives probabilities. And then you calculate the first. He didn't allow you to do the first one because obviously the first is determined as soon as all the rest of them are. But what it means is when you want that first one, you got to actually calculate it. So the set statement then calculates that first one. And then we do a COVA, which is just doing statistics on these probabilities, see what the average probability is, minimum and maximum, things like that. Okay, so what you want to do is first run this model and then go in and change it as described in the exercises.
If you don't give a name to this, it doesn't have a default, right?
There's no default. If you don't put in the option at all, then you don't have to do anything. But if you put in prob, then you have to give names. It doesn't have a default.
Names, then how do you get them?
If you don't put in the prob, what happens?
If you don't put in a prob, then you don't get, it throws away the calculated probabilities.
Just to retrieve, whenever you want to retrieve something, you just give it a name.
Right.
Okay.
And the exercises are all given in exercises.txt. So that's a text file. You pull up, it'll describe what you should do after you've run this first model.
What is the name and what is the command? The COVA is the name?
COVA is the command,
Oh, okay.
and var is the list of variables that you want the COVA done on.
Okay. And what is the name of this matrix?
What matrix?
That's the variance of variance.
Oh, COVA just says it wants the standard statistics on each of these variables. It doesn't calculate a covariance matrix. What it does is just do a mean, minimum, maximum, standard deviation of each of the variables in the list.